Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be discussing how the closed-loop control system can be analyzed in the frequency domain in the presence of disturbance and noise. So let me write the title, Feedback Control Problem in the Frequency Domain. We'll revisit the closed-loop control system, what we have done before for the aircraft attitude control problem. So let me draw the closed loop diagram. This is summing point where we are having this reference input to be tracked, and we have controller that's giving the desired control input to the system, denoted by GC of S. And we are having another summing point where control input and disturbance coming into picture. Let's denote the disturbance signal MDS. This is U of S, which is given by the controller, and the sum control input and disturbance, which is denoted by UES, going to the plant to be controlled, GP of S, and this is the output from the plant, Y of S. And this is the feedback signal. Here also we are assuming noise coming into the system, which is denoted by WS plus, and we are having feedback here, the feedback plus, and the output from this summing point, that's denoted by YMS. And the error in the presence of measurement noise we can denote as. So here, let me write EMS. This is basically measurement noise, and YMS is the measured output, and UAES is basically US plus MDS, which is nothing but effective control input to the plant. Effective control input to the plant. And this is, if you say, if you have actuator, we can say actuator input plus disturbance. Now, the measurement error we can write from the block diagram. Let me write, this is figure 1, closed loop control system. From the figure 1, we can write the EMS, measurement error, EMS. We can write RS minus YMS. Or we can write RS minus ys minus ws. And also we can write es minus ws, where es basically rs minus ys, which is basically tracking error. Now we'll find us from the block diagram from figure 1, us from figure 1, us we can write equal to gc of s rs minus ys minus ws, or okay, also you can write y of s, we can write gp of s into s2 control input. Oh, also we can write into ues, or we can write gps us plus mds. If you expand this expression, we can further write gp of s, gc of s, we can write rs minus ys minus ws plus gp of s and mdms. Again, you can write y of s 1 plus gp of s gc of s equal to gp of s gc of s into rs minus ws plus gp of s mds. So here actually we are going to find the overall error. How we can find the error due to the reference signal, and if the disturbance and noise will combine them. So this is how we are deriving. This is already you have done, but here actually we are going to find y of s equal to, can write gp of s gc of s 1 plus gp of s gc of s into rs minus ws plus gp of s 1 plus gp of s gc of s into mds. Now we can find the tracking error. Can find E of s equal to R of s minus Y of s equal to, we can substitute the expression of ys in this expression. This, let me denote the equation number 1. If you substitute equation number 1 in this expression, we'll have 1 minus gp of s gc of s 1 plus gp of s gc of s into R of s plus gp of s gc of s 1 plus gp of s gc of s into ws and minus GP of S 1 plus GP of S GC of S into MDS. So this is how we can write the overall error in the system with respect to reference signal, noise, WS, and disturbance, MDS. And if you denote G naught of S for the unity feedback system, we can write GP of S, GC of S. This is basically open loop transfer function. This you already have explained. And in terms of G naught of S, we can write equation number 2. We can write equation 2 can be written as E of S equal to 1 by 1 plus G naught of S RS plus G naught is 1 plus G naught of S WS and minus GP of S 1 plus G naught of S MDS. So this expression already you have found while we are discussing on the how we can neglect the steady state error in the system. But here the combined equation with respect to reference signal, omega S and MDS. And this expression we can write in simplified form ERS plus EWS and EMDS. So this is the first term. This is how the error and reference signal are connected or related. The second term, how the error and measurement noise are related. And the third term, how the disturbance and error is connected. So from this, let me denote this equation number 3. Here we can write where E of R is equal to, can write 1 plus G naught of S RS. So this is how the reference signal and error are related. And EWS, we can write G naught of S 1 plus G naught S WS. This is how the error and measurement noise related. And the third term, EMDS equal to, we can write minus GP of S 1 plus G naught of S. Yes. Now, if you'd like to write the measurement error equation, we can write now EMS. Basically, EMS in the control system, the block diagram we have considered here, only EMS is there. This is the EMS. So EMS we can write now. Our main aim is how we can neglect EMS, how we can make ES or EMS to 0 as time tends to infinity. So once we achieve this condition, our control system can track the reference signal in the presence of disturbance and noise in the system. So EMS we can write ES minus WS. Or if you substitute ES, what you have found here, if you substitute equation number 3 here, we can write 1 by 1 plus C naught of S into RS plus G naught of S 1 plus G naught of S minus 1 WS and plus can write minus GP of S 1 plus G naught of S into MDS. Let me denote this equation number 4. Now we can find the overall control or the control input given by the controller. We can write the control input given by the controller. We can write US equal to GC of S and EM of S. This is you can find from the block diagram. So here we can write U of S equal to GC of S into EMS. So you can write. So if you substitute the expression EMS in this equation, we have the control input given by the controller. If you substitute equation number 4 in this equation, have GC of S 1 plus G naught of S into RS plus minus GC of S 1 plus G naught of S into WS and plus minus G naught of S 1 plus G naught of S into MDS. If you look carefully, this expression, the first expression we can write URS, and second term we can write UWS, and third term we can write UMDS. So this is basically the first term URS, basically the relation between the control input and the reference signal, and second term relates the control input and measurement noise, and the third term relates between the disturbance and control input UMDS. So now where we can write URS equal to, we can write C of S 1 plus C naught of S RS and UWS minus GC of S 1 plus G naught of S and UMDS can write minus G naught of S 1 plus G naught of S. And let's denote this equation number 5. So this is how we can find the control input and measurement error equation. And our motivation is how we can neglect or mitigate the disturbance and measurement noise with designing suitable control algorithm in frequency domain. And before we proceed to that part, I'd like to highlight a few important points which are very useful for designing controller in frequency domain. As a control engineer, ideally, we'd like to have our objective is ERS should be 0, EDS should be 0, and EWS, instead of EDS, we can write MD, EWS should be 0. Once you achieve this condition, we can track YS to RS. So, but it is not possible to have this condition, it is quite difficult to achieve this objective. For this, if you would like to go to certain range or certain value close to this condition, it should be noted that first point is the disturbance, it should be, this is very important point while designing the control algorithm in frequency domain. Noted that the disturbance should be rejected, we can write disturbance should be rejected having relatively slowly with time. So it means the disturbance signal coming to the system varies very slowly with time. So, or in other words, you can write the disturbance signal have low frequency content. This is very, while designing the control system, we need to consider this point. Disturbance signal varies slowly time. And second point, the measurement noise typically varies rapidly with time. The MDS has high frequency content. This is very, very important to design the control system. How we can neglect the measurement noise with suitable design of control algorithm. Or also we have another point. In addition to this, we need to consider ERS and EMDS over low frequencies to ensure good reference signal tracking, because our main motivation is how can track the reference signal and disturbance rejection. It means our reference signal also varies slowly with time. So that's why ERS and EMDS over low frequencies to ensure good reference signal tracking and disturbance rejection. And while EWS only needs to be considered over high frequencies to ensure good measurement noise attenuation. So this is important point while designing the control system. How we can design the suitable control algorithms such that over low frequencies, it can reject the error, tracking error, and the error due to the disturbance. Now, let's stop it here. We'll continue from the next lecture how we can choose the control transfer function or controller in such a way that this condition can be achieved.